This is the next video on acid-base titrations. In the last video, we did calculations to find the pH for a strong acid, strong base calculation at several different points. And for this section, we're going to do the same thing for a weak, strong system. So here's the page where we outlined our plan on how we were going to solve for the pH in each of these different regions. And we're going to do an example of those calculations to help you on your homework. Okay, so similar problem. We have 150 milliliters of 0.2 molar weak acid this time. And we have a varying amount of 0.15 molar strong base, just like last time. The Ka for the weak acid is given, 1.5 times 10 to the negative 8th. And we are given 5 different volumes to find the pH at. So we'll start with volume equals 0 milliliters of hydroxide added. And if we haven't added any of the titrants, that means we are at our initial point. So the only thing in the system in the flask is the weak acid. And if the only thing in the flask is weak acid, we know we have to do an ice table. The ice tables have acid ionization equations at the top. So it's going to be HA plus water goes to conjugate base plus hydronium. And we leave out water. So initially we have 0.20 molarity of acid. We have 0 of the conjugate base and approximately 0 of hydronium. And we shift to the right by some small unknown amount. And we need to figure out how much we shift to find the pH. Acid dependent. Okay, there's our numbers. We can set up a Ka. That's going to be x squared divided by 0.2 minus x. And we're going to assume that x is small. So we'll write it again. X squared divided by 0.2, because we were ignoring this number. And our Ka was given in the problem, 1.5 times 10 to the negative 8. We can solve for x, and that should give 5.48 10 to the negative 5th molar. And we'll check our assumption. 5.48 times 10 to the negative 5th divided by 0.2 times 100%. And you will find that that is less than 5%. So our assumption was valid. We are good to go with that number. All right, and now that we have our x value, now we need to find hydronium concentration and plug that into pH. Okay, so x is equal to hydronium. We can just plug that straight in, and we should get 4.26. Oh, I didn't draw a plot for this one. All right, we'll draw a plot at the end then. All right, part B, volume equals 50 milliliters of base. And we are thinking to ourselves, this is probably the buffer region because a little bit of hydroxide has been added, but not a lot. But we need to make sure that we check. Okay, so we need to find moles of each part to find out. So 0.15 liters times 0.20 moles per liter. That equals 0.03 moles of acid. And we'll do the same for the base. So we have 50 milliliters. Molarity is 0.15. And that gives us 0.0075 moles of hydroxide. So the number of moles of hydroxide is less than the moles of acid. So that tells us we are before the equivalence point. And to verify that this is going to be in the buffer region, we can do, I guess we'll need to use the number of moles of HA and A minus, which comes from the next table. So we'll do our DNA table. Move that up a little bit. Okay, our DNA table is a neutralization table. So we're neutralizing our weak acid HA with our strong base hydroxide that goes all the way to completion to form conjugate base and water. And we don't include water in the table. All right, we've got 0.03 moles of HA. We've got 0.0075 moles of hydroxide. And we initially have 0 moles of conjugate base. We want to take our strong piece to completion. So we use up all the strong base until it reaches 0. We subtract it from the other reactants and we add it to the products. And we add down to the bottom. This is going to be 0.0225. Okay, so all the strong base was used up, and then we can take the ratio of these two things to check and make sure we're in the buffer region. 0.0075 divided by 0.0225. And that equals 0.33. And 0.33 is less than 10, greater than 1/10. So we are officially in the buffer region. Amazing. Okay, if we're in the buffer region, good news, we can use Henderson-Hesselbach instead of doing an ice table for the next step. Henderson-Hesselbach is pH equals pKa plus the log of that ratio that we just found. And again, technically it is in concentration of A minus over concentration of HA, but since they're mixed into the same solution, they'll have the same volume over same volume cancels out. So we can just cheat and use moles. However, we do need to find the pKa. We were given the Ka up here. So remember that the pKa, the P function means you take the negative log of that thing. And we have the K and we want to find the pKa. So we'll do negative log of 1.5 10 to the negative 8th. And we should get pKa equals 7.82. So now we can go ahead and plug that in. And we have this fraction that we already calculated, and we can plug that in here. So pH equals 7.82 plus log of 0.33. And we get 7.34. All right, on to the next page. We've done initial point, we've done buffer region. We still have 3 more. This is just going to be a very long video, so we can do the whole problem in one video. Part C. volume equals 100 mils of base. So we know that the last point was within the buffer region. This point is even greater, so it could be in the buffer region still, or it could be the equivalence point. So we need to find the number of moles to find out. So we have 0.1 liter of 0.15 molar base. That's going to give us 0.0150 moles of base. And that number is less than our 0.0300 moles of acid. And if we look very closely, we'll see that it's not only less than, it's exactly 1/2 of. So the amount of hydroxide here is equal to 1/2 times the amount of weak acid. So we are at a special point. We are at the midpoint, halfway to the equivalence point. And at the midpoint, we know that pH equals pKa. And we found that in the last video, pKa, or in the last page, was equal to 7.82. So if you notice that you're at the midpoint, you can save yourself the whole DNA table and Henderson-Hasselbalch routine. Just make sure you calculate the moles correctly. Letter D is 200 milliliters of base. Okay, we are even greater than 100. We have got to be at least at the equivalence point, if not past. So let's find out where we are. So we need to get the number of moles. As you can tell by now, that is always the first thing that we do. Unless we are at the initial point where we know for sure that there are 0 moles of the titrant added, we always start by finding the number of moles of each piece. Okay, so we've got 0.03 moles of base, and we remember that's the same amount as the number of moles of weak acid that we started with. And if the number of moles is equal, we are at the equivalence points. How glorious. Unfortunately, when we have a weak acid in the system, it is no small feat to find the pH at the equivalence point. We can't simply assume it's equal to 7. We have to do a DNA table, an ice table, and then solve for pH. So we have a long process ahead of us. So we'll start with the DNA table so we can figure out what the neutralization produces. So we have a weak acid, HA. It's neutralized by strong base, OH minus. It goes all the way to completion to produce a conjugate base and a water. Probably should have left a little more space there. Sorry, guys. We don't include water in our picture. So now we have 0.03 moles of weak acid and of strong base. Initially, we don't have any of the weak acid and we don't include water. So in this case, we're going to use up all of our strong piece, going to use up all of our hydroxide to 0, and it's also going to use up all of our weak acid. So both of these things are gone. But remember, there's not nothing left in solution like there is with a strong base, strong acid, because when you neutralize the weak acid, you make weak base. So we still have to add 0.03 moles of weak base that we produced. So there is still something in the solution, and unfortunately that something is a weak base, and that means we have to do an ice table to find out the pH of the solution. So let's put this back in molarity. So 0.03 moles of conjugate base divided by the total volume, which was 200 mils, plus the 150 mils of acid. That gives us 0.0857 molarity weak base. All right, so we've got our molarities. We're ready for an ice table. This is actually the longest calculation process for any of the different regions. Okay, and we're going to do an ice table for a weak base in water. So we need a base ionization reaction. Weak base plus water goes to weak acid and hydroxide. You're going to know these reactions in your sleep. Don't include water. All right, we have the molarity from our calculation, 0.0857. We don't include water. And then both the HA and the OH minus went to 0. All of those were neutralized. They were used up in that neutralization reaction. So all we have in the solution initially is the weak base. It pushes towards the product side by some small amount, which we need to find. All right, so we need to throw this into an equation, and this is one of the first times we've used a weak base. So when we're doing a base ionization, for our ice table, we need to use a KB, and that is going to be equal to x squared over 0.0857 minus x. And we're going to assume x is small, because that's what we do when we're trying to save ourselves some work in a super long problem. So we'll assume x is small, leave out that term. KB equals x squared over 0.0857. And here's something we haven't had to do before. We need the KB. All we have been given is the Ka for this weak acid. So what we have is this weak acid has been neutralized and it produced its conjugate base. So we need to use this Ka to find the Kb. So remember that these guys are related. Ka times Kb equals Kw. So our Ka was 1.5, 10 to the negative 8 times Kb, and our Kw at 25 Celsius is 1 times 10 to the negative 14th. That's a constant value that you should know. We can solve for our Kb to be 6.7 times 10 to the negative 7th. And we can even take a little pit stop here and compare the sizes. So our Ka is 10 to the negative 8th, and our Kb is 10 to the negative 7th. So we can see that this example problem that we're doing is actually slightly basic. So our conjugate base is slightly more basic than our conjugate acid is acidic. All right, 6.7, 10 to the negative 7th. So we can solve for x pretty simply here because of our assumption, and we get 2.39 times 10 to the negative 4 molar. And we'll check our assumption. We're feeling pretty confident though. Oops, that's not the right number. 2.39 times 10 to the negative 4th per x divided by our initial concentration, 0.0857 times 100. And we find that that number is less than 5%. So our x value is okay. And we review what we're actually trying to do because it's been so long I can't remember the pH. We're trying to find the pH. So we have x, which is the amount of hydroxide. So we need to find POH, and then we need to find pH. So POH is the negative log of the hydroxide concentration, and hydroxide concentration is equal to x. You can throw that in. That equals 3.62. And the pH equals 14 minus the POH. And so we should get 10.38. Let's check to see how we're doing and make sure our answers look reasonable. We had a pH of 4.26, and then 7.34, and then 7.82, and then 10.38. So those numbers are all increasing, as they should be, as we're adding more and more base into the system. All right, we've got one more part E to do, and then we'll draw our pH versus titrant plots. All right, part E, last part. This is the addition of 300 milliliters of hydroxide. I wish I could tell you that you do each of the different points the same, but if that was true, it wouldn't have taken me 40 minutes to teach you how to do this kind of a problem. At least this part's the same. First thing we always do is define the number of moles of each of the different parts. So 0.0450 moles of hydroxide, and that is greater than the moles of acid, which is 0.03. So if we have more strong base than weak acid, that means we are in the strong base region. So we need to do a DNA table to calculate the neutralization, and then we can continue on with our lives to find the pH. So we've got a weak acid, HA, which is neutralized with a strong base, OH minus, goes all the way to completion to form weak base and water. And we don't include water. Okay, we've got 0.03 moles of acid and 0.045 moles of hydroxide. We don't initially have any conjugate base. We are going to neutralize as much of the strong piece as we can, which is this one, but we see that we cannot actually use all of it up because there's only 0.03 moles of weak acid. So we use up as much as we possibly can, which is 0.03 moles. And then we add that to the other side. So we use up all of our weak acid this time. There is a little bit of strong base left, and there is also some weak base that we've made. So in this case, instead of neutralizing the strong piece, there was so much strong piece that we didn't have enough acid to neutralize it all. We're outside of the buffer region. And now we've got a strong base here, and we've got a weak base here. So technically, both of these are bases. Both of these produce hydroxide and water, but this is a weak base, and weak bases don't contribute as much as a strong base. So we're only going to consider the strong base, and we're going to say the weak base contribution is going to be so small, we'll just ignore it. So we'll just pretend that all we have left is hydroxide at this point. So we'll put that in molarity, and we will be on our merry way to the pH. So we have 0.3 and 0.15 from the acid. That gives 0.01875 molarity of hydroxide. And then we can use that to find the pOH and the pH. Negative log of hydroxide, in we go, 1.73, and our pH, which is equal to 14 minus the pOH, should be 12.27. And again, if this makes you feel uncomfortable to ignore the weak base, you are free to do the ICE table. Go ahead and do the ICE table for the weak base, plug in this number for weak base and this number for hydroxide, and you can push it to find the true amount of hydroxide formed at equilibrium. But that number should be pretty close to this number, and you'll see why we skipped that step if you do it. Okay, so then let's finish off by drawing our picture to look at where each of those points are that we found. So we had pH versus titrant added, and our titrant was strong base. This is a weak acid, strong base curve, so we're going to start a little higher. We're going to have a little flat part, a steep part, and a tapering off at the end. And then let's go back and find our numbers to add. So our first number at 0 milliliters, the pH was 4.26. Okay, our second point was at 50 milliliters, and we had 7.34. So let's do 0. We know our equivalence points. We'll just cheat and do that one. Was it 200, 100? Want this to look semi-realistic after all. All right, here's 50. I've already forgotten the number. 50 milliliters, pH of 7.34. So here we are. This graph not drawn to scale, for sure. Then when we got to 100 milliliters, we were at the midpoint. We were at 7.82. So you can see that between 0 and 50, there was a pretty significant pH change, even in my poor drawing. And then with the same volume addition between 50 and 100, the pH only changed by half a unit. So this is the buffer region where it resists pH change. Our next point was volume equals 200. The pH was 10.38. That's at our equivalence point. pH has shot up. And then our final number was at 300 milliliters. We were at 12.27. So this graph is not exactly drawn to scale, but you can still see that this change in pH was much greater than this, and that this change in pH was much greater than this. Okay, that is everything you need to know to use DNA tables, ice tables, the formula for pH and pOH to find the pH at any point in a titration of strong, strong, or weak, strong. And that is the end of the acid and base chapter.